we're going to look at some boiling points of materials to discern about intermolecular forces. The idea is that the stronger molecules are attracted to one another, the more energy you have to put in to pull them apart. And in the boiling process, molecules are being separated from one another. So let's first look at some comparisons between polar and nonpolar diatomic molecules. Here are the boiling points of 4 materials. On the left are difluorine and dibromine. Since these molecules are symmetric, having the same atom at both ends, they are nonpolar. On the right are hydrogen chloride and iodine monochloride. Since these molecules are asymmetric, having different atoms with different electronegativities at the 2 ends, they are polar. Let's first compare difluorine with hydrogen chloride. Hydrogen chloride boils at about 100 kelvins higher. F2 weighs 38, while HCl weighs 36, so there shouldn't be any effects due to the speed of molecules in the gas phase. So why is the boiling point of HCl so much higher? Let's think about the attraction between molecules. F2 is nonpolar, so when 2 F2 molecules are next to each other, there doesn't appear to be any reason, based on charges, for the molecules to attract. HCl is polar, so when 2 HCl molecules are next to each other, the positive end of one can attract the negative end of the other. This force of attraction between 2 partial charges is called a dipole-dipole force. Because of the additional attraction, 2 HCl molecules should be harder to pull apart, and we observe a higher boiling point. The other set of data, with Br2 and ICl, show a similar effect. The polar ICl has a higher boiling point than the nonpolar Br2. With diatomic molecules, it's easy to see if the molecule is polar or nonpolar. We've seen the same distinction with polar and nonpolar bonds. For a molecule to be nonpolar, it needs to be what we call symmetric. The 2 ends are the same. A polar molecule is asymmetric. The ends are different. For molecules with more than 2 atoms, the symmetry requirement is the same, but it can be harder to see, especially when we are looking at Lewis structures. A polar molecule will have a positive and a negative end, so it has to be different in at least one axis. Essentially, we are looking at the disposition of atoms around a central atom in a molecule. To be symmetric, and therefore nonpolar, all of the electron groups need to be the same, and all the terminal atoms need to be the same. The idea is that the molecule is the same, charge-wise, in every direction. You can't find a positive and a negative end. In order to be polar, you need a difference in some direction. Either you need the electron groups different, or terminal atoms different. If resonance is present in a molecule, we have to be careful and consider the actual bond orders, which may be fractional, and not just look at only one resonance structure. A couple of examples should help. First, carbon dioxide. We show one of the 3 resonance structures, but considering all 3, the CO bond order is 2. In this case, the electron groups are the same, both double bonds. The terminal atoms are the same, both oxygen atoms. That makes the molecule symmetric and therefore nonpolar. Sulfur dioxide has 2 resonance structures, one of which is shown here. In this case, the terminal atoms are the same, both oxygen atoms, but the electron groups are different. Now, be careful with resonance. The 2 bonds are actually the same, both with a bond order of 1.5. But the presence of the lone pair on the central atom makes the electron groups different. This molecule is asymmetric based on electron groups and therefore is polar. It is important to know that we are looking at the overall polarity of the molecule, not just the individual bonds. In carbon dioxide, the individual bonds are polar. Oxygen has a larger electronegativity, so they are polarized toward the oxygens. but both oxygens are partial negative. The molecule does not have a positive end and a negative end. There are polar bonds, but they cancel out. If you think about adding vectors, there would be no net polarity. In sulfur dioxide, the polarity can be more easily seen if we draw the structure bent. Again, we have two polar bonds. Their effects cancel out left and right, but they do not cancel out up and down. There is a net polarity toward the bottom of the molecule as drawn. Here we have polar bonds that don't cancel out.